And here, of course, I like this picture a lot. It's drawing from Lars Hansen book from Cyprus. And it kind of illustrates the three camps in economics. There are some numbers, some years, but I don't think it's actually time related. I think they all exist at the same time, even now. So you can kind of recognize this guy, classical control, classical economics. It's very clean, very beautiful theory, the equations, contraction mapping, all these beautiful formulas. Very, very clean, very beautiful. Those guys kind of later with big computers, with Bellman equation, they start modeling, they start producing tons of outputs, which no one really can understand really well, the kind of models they were running, and it doesn't have to be really applicable to real cases. And then it's very unsatisfied guys kind of place with, it's the idea that the models are as bad as the data are. It's not that just the data, by definition, you have to be really careful, you have to do very good econometrics on data, but you also have to be very careful with the models that you're using. The models are often misspecified, so you have to treat the models as another source of your data. You don't treat the model as the eternal truth. You don't have a true model for the phenomena that you study. So the model is just another data generating mechanism in addition to what you observe, because sometimes you cannot, most of the time in economics you cannot conduct experiments all over again. You have one set of data, that's it. So you have to use the model in order to produce some counterfactual set of data and to see what you can release. Now, all these quotes, I put a lot of quotes. It doesn't mean that I agree with all of them. And those three quotes are from basically this crowd. Why this crowd seems to be the most unsatisfied? Because they were actually on the front lines. They were really dealing with some quantitative problems for a very long time. And while those guys are creating those beautiful kind of structures, they were most often, those guys were kind of on the front lines. They were taking the bullet for most of the people, especially quantitative finance, people with quantitative finance. So what they see all over the time is that this problem is a lot of folks regular style mythos, Oxfords and Lemonson numbers tends to be inversely proportional to the efficiency rate. It kind of ring through, and of course this quote is especially interesting because, and then if you have a model, good model, if you have like 50 pages of mathematical symbols, I mean it's good for you, but how I will put that to real use? If I'm a politician and you come to me with this model, I don't understand anything with it. I need to play with it and see how it helps me to make sure that I actually understand what's going on. And surprisingly, politicians are really interested in this stuff. And if you come to them and you can just, you cannot anymore talk to them in generalities. You cannot talk that this will work because, well, I swear it's true. You have to come up with numbers, you have to come up with models, testable models that can be tested independently, can be verified independently. And most often those kind of models are not easily, cannot be easily put into quantitative tests. It takes a lot of efforts to take them from abstract level to more applied. And you do need data, you do need database, good input script and calibration, because otherwise they're still in this academic reality and not very useful for real application. Now, this advice is kind of, I would take it with a grain of salt a little bit, because most often the kinks in the model is what makes the model interesting. Now, what happens most usually in real life, it's like you go to work, you get some wages. It's very boring, but it can be modeled really well. There is no problem in modeling this kind of phenomenon. So there is a kind of conundrum. The most interesting things is the things that it's really, really difficult to model. So it's when, for example, your company goes bankrupt and you start your new company, you get rich. That's what's interesting. That's what's drives the economy into some interesting stage. But that's incredibly difficult to model because, for example, like you can have 20 years you work fine, and then something happens in one day, and suddenly you make a transition into a completely new activity. And that's what we are trying to actually do here in this project. That's what we are trying to model. We're trying to model transition in occupational choice, people to make some decision that affecting their life greatly. So it's not like gradual transition that happens over time gradually. And of course, there are lots of choices that people make in their life, and there is only tiny percentage of the people who make these active choices. And if you look at this, if you have a huge bulk of economy that skips something happening, but it's happening very slowly. It's a lot of noise, and only some tiny percentage that's actually making the choice of becoming an entrepreneur or go to the city from agricultural village, from a far remote village and be successful. That's what we're trying to do, and that's really hard. And that's where the kings actually hit. And when the kings hit, your beautiful numerical algorithm, it converges really fast, which works very good, very perfectly. That suddenly they don't work because they hit the kings. They're not working anymore. Okay, so this is very basic description of the most useful tool we have in economics. And why I put it here, it's really very basic. You basically start studying economics with this equation. Because I want to stress that this equation was not particular to economics. This equation is known under many names in many different disciplines, and it was actually first formulated in 1927. And this was related to the control program for the rocket engine. So basically, when you launch a rocket and you want to hit a certain target, once you launch it, you have a certain storage of fuel on the rocket, and you cannot do anything. The rocket can decide how to adjust the fins and whatever, but you're still limited by this fuel storage. There is a turbulence in the atmosphere, some shocks happen, but you still have to hit this target, right? So you have to write a certain program that allows the missile to kind of make a right decision under unknown turbulence in order to hit a specific target. So that's what actually happened in economics, but compared to this case, now we don't know the target. That's the problem. So imagine that you want to hit like Osama bin Laden, but you don't know where he is. That's what happens in economics, right? So what you start bombing or not. So, but still, it's a huge problem compared to classical mechanics, compared to robust control theory solved by PTA. You don't have a boundary condition. That's a huge problem. And you can have possibly many infinite number of solutions.